Alright, ladies and gents, welcome back. We're in 8-7, Indeterminate Forms in L'Hôpital. So we haven't done La Hospital's rule this semester, this class in BC yet, and you're probably wondering, like, when were we going to get to it, because it wasn't on anything for any derivatives that we've done so far, but we're going to get to it right now. I'm not really sure why it's in Unit 8, but it really doesn't matter. It's pretty easy to do, and I think part of it is it's using limits, so kind of get back into the limit aspect a little bit, because we're going to do some limits in the next two sections, and this might help in that instance. So I guess let's get moving. So an indeterminate form of a limit occurs when you attempt to evaluate the limit and find that it produces a fraction, either 0 over 0 or infinity over infinity. And in order to evaluate it, we have to simplify it in some way. Well, in the first section on limits, we did this by factoring, or we did this by multiplying by a conjugate, maybe simplifying or whatever. And so, for instance, if we look at this, okay, this is the same as the limit as x approaches 0. E to the 2x minus 1 is actually e to the x minus 1 and e to the x plus 1 over e to the x minus 1. And so, because I can cancel, right, those get canceled. So this is the same as saying the limit as x approaches 0 of e to the x plus 1, which if I plug 0 in, right, I get e to the 0 plus 1, which is 2. Right, this is 1 plus 1 is 2. So we can do that. All right, some, like most of them, will be nice if we can do that, but some of them will not factor. And so if I look at that limit there, it will not factor. There's really nothing we can do. And if I write it as e to the x minus 1 and e to the x plus 1 over x, like, it doesn't do anything. And so that's where L'Hôpital's rule, or La Hospital is one other way you can pronounce it, right? You guys remember from last year. And that's where we get. So when I get some indeterminate forms, for the most part, it's 0 divided by 0 or infinity over infinity. But you could also get 0 times infinity. That's another one. And we're going to get to one of those as well. And also an indeterminate form is like 1 to the infinity. Okay, so these are more popular and more prevalent. These are very minimal, like you're not going to see those very often. So really, if you just know how to do these two, then you're going to be okay. So it basically says that if x is approaching some value of a function divided by a function, then if I get one of these forms, then I can take the derivative of f, still on top, I can take the derivative of g, still on the bottom, and then plug in the value c again. And then if I keep getting 0 over 0 or infinity over infinity, then I got to keep going and keep doing it. So let's move on. Let's some examples here, and let's see if you remember. So if I look at this, okay, if I just plug in, just substitute, okay, this is really equal e to the 2x minus 1. That's going to be 1. 1 minus 1 is 0, and then 0 is on my bottom. So then we're going to use La Hospital's rule. I'm going to put L'Hôpital, but you can put La Hospital, it's fine. So his rule says that I'm going to take the limit as x approaches 0, so the same value, but the derivatives now. So the derivative of the denominator is pretty easy, that's just 1. The derivative of the top is 2e to the 2x. Okay, now if I plug in 0, that's just going to be 2, right? 2 over 1, so that's the answer is 2 there. And that's all I get there. This one here, if I plug in infinity, so as x approaches infinity, now we can also think about this, if you remember from horizontal asymptotes, okay, if I remember from horizontal asymptotes, that I can look at what grows bigger. Okay, and in this case, x and x, x and ln of x, they're going to grow pretty much at the same rate. The ln of x, remember, kind of goes like this, and this x here is going to go like this. But at infinity, like, they're going to be, for the most part, they're going to be within reason. Like, you don't really know which one's growing more at infinity. Probably x, but probably not. Okay, so x actually will grow more than infinity. So if this is infinity and this is going to be bigger on the bottom, then we know this answer is probably going to be 0, right? If it's bigger on the bottom, then it's going to go to 0. But I'll show you using L'Hopital's rule. So because they both go to infinity over infinity, then let's take the derivative. So this is the limit as x approaches infinity. The derivative of 1 over x is, or the derivative of ln of x is 1 over x. The derivative of x is just 1. So this is equal to the limit as x approaches infinity of just 1 over x. And if I do that, if I plug in infinity, I'm going to get 1 over infinity, which is equal to 0. Okay, so that's where I get that one from. So that's pretty easy. So you can do it using horizontal asymptotes whenever x approaches infinity or x approaches negative infinity. You can use horizontal asymptotes there. Okay, if it's not infinity or negative infinity, then you cannot use HA, horizontal asymptotes. So what if I have to apply the rule more than once? Well, if I look at this particular problem, if I plug in negative infinity, okay, to this piece here, I'm going to get positive infinity at the top. And if I plug it in down here, this is e to the negative of negative infinity. So that's e to the infinity, right? Which means it goes towards infinity, right? So that means I got to do L'Hopital's rule. So I take the limit as x approaches negative infinity of my derivative. So that's 2x over negative e to the negative x, which that's also going to go to, and this is negative infinity up at the top. Now it's negative infinity at the bottom. So that's just infinity over infinity. So I know I got to try it again. So I'm going to take the limit as x approaches negative infinity of 2 over positive e to the negative x. And so now I plug in negative infinity. So it's going to be 2 over infinity, right? So this is just going to be 0. And you can think of it horizontal asymptotes as well. X squared is not going to grow by near as fast as e to the negative x. So you could you probably could have got that right from here by saying I used horizontal asymptotes, and that's fine. But what happens if we have an indeterminate form 0 times infinity? So if I take infinity here, this is limit as x approaches infinity of e to the negative infinity root infinity. Okay? Well, e to the negative infinity is really 1 over e to the infinity, so this here is going to go to 0. The square root of infinity is going to go towards infinity, so we have 0 times infinity as our indeterminate form. So we can use L'Hopital's rule, but L'Hopital rule only works when I have a fraction. Okay, it doesn't work when I actually have two things being multiplied. Well, how can I turn this into a fraction? I can say, well, I can make e to the negative x in my denominator because it's negative here, so it's positive in my denominator, and therefore root x is on top. Now you could use horizontal asymptotes here as well, and we know the bottom is probably going to grow faster, so this is probably going to be 0. But if we take the derivative, this is really x to the 1/2, right? So I get 1/2 x to the negative 1/2 over e to the x. All right, and then I'm still taking the limit as x approaches infinity. I can plug in what I get. So this is going to be actually 1 over infinity, which is 0. So you're going to get 0 each way. Honestly, it's faster if you use horizontal asymptotes when x approaches infinity or negative infinity. It's just faster. Okay, and we've done practice with that, so you should be good to go. Let's go to the last one here. Let's get done with this video, call it a day, and then we'll get into some harder stuff in the next two sections. So indeterminate form 1 to the infinity, if I plug in infinity, so this is going to be the limit as x approaches infinity of 1 plus 1 over infinity to the infinity. Well, 1 over infinity, this is going to go to 0, right? So 1 plus 0 to the infinity is going to be just 1 to the infinity, which doesn't really work very well, right? So this is an indeterminate form. So what am I going to do here? Well, there's a couple things we can do. Okay, if I want to take the derivative, okay, so for instance, if I want to say that y is equal to this, 1 plus 1 over x to the x, if I say, okay, I want to take the, let's just get rid of this x up top, let's take the ln of that. So if I do that, I get x times the ln of 1 plus 1 over x. And if you don't remember the ln rules, if I took the ln of this, because this is an exponent, it actually becomes a coefficient. That's a rule for ln's. All right, so then, now what I want to do is, let's see, take the derivative of both sides. Okay, let's take the derivative of both sides. So, Do I want to do that? I'm wondering, do I want to do that? Yeah, what the heck? Let's do it. No, I don't want to take the derivative of both sides. So let's do something here. Let's turn this. Okay, so this is gonna be a little complicated, and it's kind of dumb. I don't even know why it's on here, but it's good to see where this comes from. What I want to do is I want to make this into a fraction. So turn into fraction, because then I'm going to use L'Hopital's rule. So turn into fraction. How do I turn this into a fraction? Well, we're going to leave the ln, the ln of 1 plus 1 over x up top. I'm going to put the x in my denominator, but if I put it in my denominator, I'm going to make it 1 over x, because if I were to actually multiply by the reciprocal, I'm going to get what I started with. It's just a different way to write it, because now it's a fraction. And now I want to take the limit as x approaches infinity. So this left-hand side, I'm going to leave that there for a second. I'm not going to touch that. I'm just going to leave that there. You don't have to worry about really knowing how to do this problem. It's just going to be kind of miraculous as to what we get for an answer. Okay? So now what do I want to do? Well, now I can take the derivative, right? So if I take the derivative, I get the limit as x approaches infinity of my top, the ln of all that. That's 1 over 1 plus 1 over x times negative 1 over x squared. That's the derivative of the inside. I didn't show that to you, but that's what it is. And then 1 over x is negative 1 over x squared. Okay? And now if I find common denominator, actually I can cancel those out because those are exactly the same. So this is the same as saying the limit as x approaches infinity of 1 over 1 plus 1 over x. Okay? Which, if now I plug in infinity, okay, that's going to go to infinity, which is going to go to 0. So this is going to be just 1, or 1 over 1, which is just 1. So the right side is just 1. But the left side is still there. So it's still the ln of y is equal to 1. Now, in order to solve this, I got to e both sides, right? So then I get y is equal to e. So what's interesting about this is that this piece here, the limit as x approaches infinity of 1 plus 1 over x to the infinity is equal to e. So this is a cool way to think about the value of e. I'm sorry, should be x here. This is pretty cool to think about the value of e. So no matter what x is, right, that's going to approach some value e. I just think that's pretty interesting. You don't have to worry too much about it. It's probably never going to see it again, but it's still interesting to think about. And this is, if you go into any financial analysts or something like that, they're going to use this stuff here. And this is a very popular number. Okay, that's it for this one. We got 2 more videos in this unit, and then we're going to call it a day.